1,000 degrees Celsius. However, there are places in the universe that are much different, with conditions that are unimaginable to us. There's the tiny realm of the atom in the grand sweep of the Milky Way, with temperatures ranging from so cold that air turns into a liquid to so hot that they can tear apart a star. It was with the opening days of the 20th century that scientists began to take their first tentative steps into a vast and new world, to learn about how matter behaved under conditions that had never been before investigated. It is therefore not at all shocking that surprises arose. In fact, that's an important lesson to keep in your mind. The lesson being that as soon as you step outside of your comfort zone, you should expect to be surprised. As we move ahead in our journey of trying to imagine a theory of everything, that should be your mantra. Expect the unexpected. I'll let the story tell itself, but the core idea of this lesson is an understanding of light that unifies the idea of a particle and the idea of a wave. The oldest arguments in physics is on the nature of light. Is light a particle or a wave? You'd think that'd be easy to determine. After all, waves and particles are pretty different things. Waves have wavelengths, frequencies, and amplitudes and extend over a large volume. In contrast, particles have a well-defined location without the trappings of a wave. They're very different beasts, and it seems that figuring out which of the two that light is would be an easy task. Maxwell confirmed that light is a wave, but we'll see that a fully correct answer is a lot harder than it seems. Suppose a person proposed one or the other. At a minimum, their proposal needed to explain some of the things we see light do. For example, we know that light can reflect. That's easy to demonstrate using a simple mirror. We also know that light refracts, which is the effect whereby light bends when it passes from air to a transparent solid. While early discussions began in Greek antiquity, the arguments were essentially philosophical until around the time of Newton. Newton was a proponent of the particle view. If light is a particle, it's easy to explain how light reflects. It's no different than bouncing a tennis ball off the ground. If you assume that light travels faster through a solid than it does through air, the particle idea can explain the observed bending of light as well. We now know that this assumption is exactly backwards. Light travels more slowly through solid matter than it does air, but that wasn't known at the time. It was Newton's extraordinary scientific reputation that led to the particle theory of light to be favored for a very long time. However, the wave idea had its adherents. English scientist Robert Hooke and Dutch mathematician Christian Huygens, both rough contemporaries of Newton, worked out a wave theory of light. This theory can also explain reflection and refraction, although the refraction explanation required that light move more slowly in solid matter rather than gaseous matter. We now know that this is correct. However, for about 150 years, there was no measurement to prove it. Of special note, Huygens postulated that there was a substance called the luminiferous ether, which allowed light to travel as a wave. While we no longer believe in the ether, theorists continued to talk about it into the late 19th century. The lack of any evidence for ether was an objection to the wave theory. The argument persisted until about 1800, when a series of experiments by English polymath Thomas Young demonstrated rather persuasively that light was actually a wave. Given the definitive nature of the experiment, it's worth spending a few minutes describing it. One of the properties of waves that is very different from particles is that they can interfere with one another. You can see this at the seashore when two waves cross one another, and the result is temporarily a single but larger wave. This is called constructive interference. Similarly, you can see when the peak of one water wave encounters the trough of another. The result is that the two waves cancel each other out, and this is called destructive interference. Young's experiment used an opaque barrier with two adjacent slits. When light illuminated a single slit, it passes through the slit and it spreads out. That's true of the other slit as well. Now, if light is a wave, you'd expect it to look like ripples in a pond that you see when you drop a stone in the water. On the other hand, both slits generate these ripples, which means that there would be two sources of waves. And as I said before, waves can interfere with one another. There would be spots that are peaks of one set of waves and troughs of another set of waves, which would cancel out. Canceling out light means there would be dark spots on a distant screen. Similarly, there would be places where the peaks of both sets of waves would appear at the same time, the same location, resulting in bright spots on the distant screen. That's exactly what we see, bright spots and dark spots. Young's double-slit experiment is the definitive and inarguable demonstration that light is a wave. After this experiment, the discussion